Yeah, well.
So, good morning, everyone. Let's start our first tutorial. We are really happy to see here a lot of C hackers, and that really looks cool. So, please welcome Chris Travers, and he will talk about extending Postgres in C.
Thanks, everyone, for coming. So just a show of hands, and I'll pause for a moment since I know there's translation. How many of you have ever tried to write any sort of extension code against Postgres in C before? Just a few? OK. This talk is pretty beginner level, but I try to go into a fair bit of depth in a couple of points. So hopefully both of those of you who have done this before and those who have not will hopefully get a lot out of it. So first about me, I'm Chris Travers. I head the database department at Adjust. I have had roughly maybe just 21 years of experience with Postgres, mostly as a software developer and as a user, but also more recently as a developer and even occasionally as a hacker. I got one bug fix in a little over a year ago to a race condition between parallel plan startup and replication, but it turns out to be a more general problem and a more general fix. So I've had a fair bit of experience now working with Postgres in a wide variety of roles as a DBA, as a software developer, and as a sort of database developer in the sort of things we'll talk about today. And hopefully this will be helpful to you. So I've been around the community for a long time, everything from accounting software to custom extensions and things like that. And currently, as I say, I head the database team at Adjust. We basically, the core of our business is refereeing advertising contracts. Our servers have about 500,000 inbound requests a second that we have to process and handle. And our main analytical pipeline stores right now around 1.3, 1.4 petabytes of data just in Postgres. Part of the way we do this is with a lot of C coding of the sort that we'll talk about today. So hopefully you'll find this interesting. I'm going to cover just a few topics. I kind of want to go over a quick table of contents before we get started. The bulk of this tutorial today is going to talk about how to work with Postgres' C memory management framework. If you don't understand how to deal with memory management in Postgres, you will get bitten hard and periodically, though maybe not as quickly as might be ideal, because C is a fairly low-level language, and if we don't know what we're doing and how things are handled behind the scenes when it comes to allocations of memory, we're not going to be able to effectively develop against Postgres. Then we will go through basic types and a basic type example. This is one thing we use at Adjust. It's a very simple type. It just converts a string to a very, very minimal integer representation. So you can think of it as a very compressed enum. And then we will go through more advanced types, talk about some of the gotchas that people have when they write aggregates. Then if we have time, we'll talk about foreign data wrappers and kind of go through two examples there. And so the way I've basically decided to go about doing this is to go through the examples and kind of discuss each one in depth, walking through the code and that sort of thing. So I'll try to take question breaks periodically, and if you have to get up to use the restroom or something, I'm not going to be offended if you just walk out and come back later. So first, why would we extend PostgreSQL using C? We can actually do a lot of extensions in Postgres using PGSQL, Perl, and some other things. And up until very recently, C was more or less the last thing I would look at on my list, right? So when I was working on previous projects, I did a lot of Perl to create functions that we'd then index the output of and stuff like that. But until very recently, I didn't do a lot of C. Why C? You're going to get much better performance in most cases off of C. You have much more control over how you're modeling your data in C, and you have full access to the Postgres internals. Finally, it's very memory efficient. If you're pulling stuff out of the database and you're manipulating in PGSQL or Perl, you're going through several different layers of memory allocations. And both that makes it slow, and it also kind of increases the memory footprint as you go through and work perhaps on very large data sets. So if you're trying to write very well-performing extensions that are going to perform well on a wide variety of use cases, C is the best way to go. Rust or C++ will get you pretty close. But you have a lot more wrapping of things that end up having to go on in those environments than you do in C. And in fact, one of the foreign data wrappers we'll discuss is in C++. So general problems that people run into when they try to do stuff in C, generally, and this isn't just about Postgres, but they're things that we have to kind of think about when we're writing stuff in C. C doesn't really support namespacing. And so the single biggest problem that people have, and it's one of the things that C++ tried to solve 15 different ways, is the fact that you have the possibility of linker symbols colliding, and then you get weird behavior and stuff like that. The second thing is you don't have exception handling in C. And exceptions, once you add them anyway, tend to throw your code through a loop. We'll talk about some of that later. There's no object orientation as we normally think about it, but that's fine because we don't want to think about programming in Postgres in an object-oriented way. I'll talk more about that later. Postgres forces us to think much more like functional programming and much less like object-oriented programming. And then finally, lower-level pointer management is something that people struggle with. One of the reasons I'm spending a lot of time at the beginning of this tutorial talking about memory management is just because Postgres gives you a wonderful framework for handling pointer management and things like that doesn't mean you can't mess it up. And if you don't understand what's going on behind the scenes, you will mess it up. So good thing is Postgres provides a lot of solutions to this. Within the Postgres code, you have a lot of things using dlopen, dlsym to provide sort of a namespacing of symbols into specific shared objects. In fact, when we do C language stuff, that's exactly how it works inside. Basically, when we invoke a C language function, it uses dlopen and dlsym to invoke the function. Since we don't have exceptions, Postgres provides a framework for that, including pgtry and pgcatch, elog and ereport. Those things can bite you occasionally. So again, we'll talk about some ways you can get bitten by that. Again, we don't really like to approach things like object orientation. We like to approach things much more like functional programming and pointer memory management. I took a whole bunch of portions of this from a talk I gave in Ottawa at PGCon, specifically talking about this topic, because if you don't understand it when you get involved, you can shoot yourself in the foot, but if you do understand it, it makes your life a lot easier. So in C, you have a lot of problems with memory management. I'm just going to skim over this really fast. You can have both real memory leaks, you can have fake memory leaks due to memory fragmentation, you can have double free bugs, which can happen in Postgres, by the way. You don't have garbage collection in C, but you do in Postgres. And so this is part of what we'll talk about here is how we solve these problems for you. So when we write code in C, we tend to think about allocating a buffer and then writing data into the buffer, right? If we write too much data into the buffer, we get a buffer overrun. And basically, you can think of primitive types, such as char, int, or long, as being sort of atomic fixed-size pieces of a buffer. So if we allocate a struct, we get a buffer, right? If we allocate an array, we get a buffer. And in a struct, of course, we'll have alignment issues. If we mess those up, we can get SIG buses if we're moving from an Intel chip to a RISC or something. But basically, you know, we just get a buffer and everything else is syntactic sugar around it. Well, key point of memory management is that in C is that the programmer controls where the buffer is stored. So we could allocate on the stack, we could allocate on a heap, we can take a big buffer and we can divide it into smaller buffers. There are a lot of things we can do. Very typically, people avoid using the heap. They avoid using malloc and free because that's where you get a lot of these problems. And then they basically use the stack as a garbage collector. We don't really do that a lot in Postgres. We tend to approach things differently. So as a show of hands, how many people here have done a significant amount of like professional C programming? Okay. So Postgres gives us a really important tool for handling this. It's called the allocation set. Now, an allocation set is basically a variable length series of buffers which have a managed lifetime. Okay? We could manage that lifetime. We could let Postgres manage that lifetime. We'll talk about how we let Postgres manage that lifetime. Memory in the allocation set is freed together. You can destroy an allocation set, you can create an allocation set, or you can reset it. If you reset an allocation set, the whole allocation set may be destroyed, or it might reuse a piece of it. This depends upon how you set up the allocation set when you're setting it up. In most cases, we don't set up these allocation sets. We let Postgres set them up. And most of the time, we don't have to think about them. But if we don't think about them ever, and we don't know they exist, then we just use palloc, we forget, and then at some point, we get bit because our allocation set was freed out from under us. There's also a function like palloc called pfree, and pfree will release the buffer that we got from palloc back to the allocation set. We usually don't use pfree a lot. So speaking of the chunk allocator, there's also a slab allocator that's not used by very much. But as far as the chunk allocator goes, we start off with an 8 kilobyte block. And if we run out of 8 kilobytes, we're going to allocate 16 kilobytes more, and then 32 kilobytes after that, and then 64 kilobytes. So every time we run out and we need more memory, we double the size of the next piece that we add to that chunk allocator. Does that make sense? These are basically large buffers with basically bump pointers alongside them. And then they are internally mapped to what you can think of as sort of like a smart pointer system. Block allocators, when we use pfree, what we actually do is we mark that section that we had used as available for reuse, and then we could reuse it. This is one reason why double pfree can be a problem. Allocation sets can have parents, so they exist in a tree structure. Okay? If you destroy or reset an allocation set, this cascades onto all children. Does that make sense so far? So a few practical considerations. The first few allocations end up in the heap on glibc. So you have a lot fewer malloc operations. A lot of these end up getting released back to the operating system properly. And when you get a very large allocation, these end up in anonymous segments. And so, like, if you're doing a whole lot of allocations, you're much less likely to fragment your heap on this approach than you are if you're just using straight malloc. And then, since we can sometimes reuse part of an allocation set, we can actually avoid putting a lot of things through malloc and free. This is actually a very, very highly optimized design. And if you start actually looking at how it works and start looking at what happens when you turn off a lot of these optimizations, you'll see it. So now that we've talked about allocation sets, let's talk about the sort of the wrapper concept in which we typically use them. This is called the memory context. Show of hands, how many people here have heard of memory contexts? How many people here have ever selected a memory context? A few? Okay. So a memory context is just an allocation set with a defined lifetime. Okay? So these function as parent allocation sets for other allocation sets we might create. And they basically allow us to have life cycle management of our memory in C. This gets us out of all the memory leaks and a lot of the other kinds of problems that we would typically have if we were to work with C. There is a single top memory context that survives for the life of the backend. And then you have child contexts underneath that. And they all have different life cycles. And so, like, the cache memory context you could free if you wanted to, and then all your cache plans are gone and things like that. The top transaction context, when it frees, will free all of your stuff that's like in the statement and row context and things like that. So here's the global memory contexts as a tree. It's slightly complicated because portal context could occur under message context or under top transaction context, depending upon whether you are in an explicit transaction or not. So the ones I have with an asterisk here are the ones I recommend using. I don't recommend using the postmaster context unless you know what you're doing, and I don't recommend using the message context unless you're extending the protocol in some way. Those are well beyond the scope of this talk. But the rest of this are very, very, very typically used. Then we have, in addition to the global memory context, we have certain operational memory contexts. We have per plan node, we have per tuple, and then we have special ones that kick in when we do aggregations. And then for logical replication, we have apply context and apply message context. And these use the slab allocator, not the chunk allocator. You don't need to remember all that for the logical replication stuff. But that's just a footnote. So if you're trying to read through the Postgres source and wondering why this uses the slab allocator, it's because the slab allocator was written for logical replication work. Most of the time when we write stuff, we are going to implicitly use the per tuple memory context. That means that when we go on to the next row, our memory will be effectively freed. Now, I say effectively because we may actually reuse that first 8K block. And that can come back and bite us in some not very nice ways. But we will reuse that 8K block. So in the per tuple context, we start off with an 8K block. When we reach the beginning of the next tuple processing, we reset it, and we reset it back to that first 8K block. So we reuse that first 8K block over and over again. So we completely avoid using malloc if we only have a relatively short tuple. and most memory lives on in the heap. We really have very little that ends up going through glibc memory management. It's just simply reusing the existing allocation set that we have. Notes on aggregates. You're going to note that one difference between a per tuple and an aggregate is that your aggregate is going to have some stuff that has to persist between tuples, right? If we're doing a sum, we can't just clear our sum every row we go on, right? So we actually end up with a special we use a special aggregate context, and the aggcheck call context function returns a pointer to that context. So if you're writing aggregates in C, and you're doing anything with pass by reference types, which we'll get to in a moment, you will almost certainly want to use the aggcheck call context. You pass in an argument, so you can see the call here, where it says aggcheck call context fcinfo. That pointer to that address to the ag context is where it will then write the pointer. Otherwise, we could accidentally allocate memory in the tuple context. And there are certain cases where you can do this in a way that all your tests are going to pass, everything's going to look great, then you roll it out to production and either you corrupt something in your database or you get garbage results back and nothing makes sense. It doesn't make sense because you're using memory that's been reused and it's being clobbered by something else. Now, if I've scared you off from that, then just go into aggregate creation a little bit cautiously, and you'll be fine. So the other thing that's really important to recognize at first is how pfree works. When we use palloc, we get back basically a pointer to the start of our buffer, right? Before the start of the buffer, we have a void pointer which points to the memory context, or the allocation set. So when we pass to pfree, we actually subtract the size of a void pointer to find the memory context pointer, and we use that to get to the map of free space and things like that. If you pass a null into pfree, you'll get a wraparound and you'll get an access violation in Windows or a segmentation fault in Linux because it'll wrap around into kernel space. I was actually having a conversation with Tom Lane about this, and I asked, why is it that free returns null when you pass in a null, but pfree crashes when you pass in null? And he said, well, we decided a long time ago that this was a really easy way to find bugs that we would have never found and never fixed. So take that as a wonderful note, and if you start getting segmentation faults, especially if they look like they're an integer wraparound of address space, this is where you look. So I want to talk quickly about best practices here, and then we'll start to get into examples. So for best practices, know your difference between palloc, palloc0, and memory context alloc. These three are very important. They have different values. They should be used in different places. Palloc is just like malloc, but it gives you that lifecycle management, right? So at the end of X amount of work, that allocation is going away. Palloc0 does extra work. It zeroes out your buffer for you. Okay? So if you want to just assume that pointers in a struct are allocated to nulls, palloc0 is probably what you want to use. One of the key differences between palloc0 and calloc is that if you do a big allocation with calloc, Calc is going to do a wonderful optimization in that it's going to map in a 0 page, and then on your first write, you'll take the hit of actually writing that data out because you'll do copy on write. Palloc 0 can't do that because we're working inside an already allocated buffer. So we're going to take that hit right at the beginning. And then the final one that you should be aware of is memory context alloc. Memory context alloc allows you to specify the memory context in which you're making an allocation. So when we talk about the foreign data wrappers, one thing we'll talk about is why we particularly allocate certain things in, say, the top memory context or the cache memory context. If we need to do that, that's exactly what we would prefer to do. It's much better than switching memory context to top memory context and then doing a bunch of allocations. So if you're having to allocate something outside of where you'd normally allocate it, or to a different lifetime, that's the one you would use. Best practices for aggregates. If where something's allocated matters, always use ag check call context. Let me explain to you why this is important. Suppose we have a per row memory context. It's 8K, right? We've written an aggregate that has to allocate some memory somewhere. And we forget to allocate it to the right memory context, and so it goes onto the tuple memory context. Now I write my tests. And in my tests, I have a table. It has 4 integer columns, and then it does some aggregates. What's going to happen? As we allocate those integers, we're going to allocate those on the per row context, right? So that's what, 32, let's say 64 bits per attribute for the void pointer plus, well, let's say 64 bits including alignment, so that's 128 bits times 4, we're up to 512 bits, we're way short of 8K. Every row that we do, we're going to come back and we're going to reuse that same 8K block. All those values for the rows are going to get rewritten properly, but our pointer is still going to be pointing to memory that seems like it works for us. And so all our tests are going to pass. We'll talk in a moment about how to get around that so that your tests can fail when you want them to fail. But at that point, everything will seem to work. Then you go in, you write a query, and it has a text field and then an aggregate. And a text field is variable length. And as long as your longest field's out at first, everything works. And if you have the shortest field first, then the later fields are going to clobber your aggregate data, and you're going to get garbage out. So you want to use this, and you want to switch to the appropriate memory context if you're having to do any allocations inside your aggregation. So the second thing I want to talk about here is use of cached memory context versus top memory context. Basic rule is things that need to be cleared together belong together. If you're never going to clear something and something should never be cleared, then sure, put it in top memory context. If you might need to clear it periodically and you'd invalidate cache stuff, put it in its own context underneath cached memory context. And in most cases, you probably don't want to put it straight in top memory context anyway. You probably want to have your own memory context, which is a child of top memory context. So you can reset that one without resetting the top memory context. Does that make sense? Is there anybody for whom this does not make sense? Secondly, avoid creating your own top-level memory contexts. Yes, you can do this. You can create as many memory contexts without a parent as you want. But it's really hard to track in code, and it means that certain things might not happen the way you want them to happen. So it's much harder to reason about things when you don't track the parents. Furthermore, there is simply no reason I can think of why you would ever want to have a top memory context instead of your own child of a top memory context, because top memory context will never be reset anyway. This just simply tells you this is effectively part of that life cycle. Finally, this is the single most important advice I can give you going forward. When you start trying to do this in production, please have a test instance where you have compiled Postgres with enable cassert. Cassert does a bunch of very important things. The first thing is it enables a whole bunch of sanity checks everywhere in the code. And so if you violated something small, you'll get an assertion failure, and Postgres will crash. Much more importantly, when it resets a memory context, it zeroes it out. You don't want to do this in production because that's an expensive operation, right? But remember what I said about aggregates and wrong memory contexts? This will turn that difficult to reproduce bug into an always crashes bug. And that's exactly what you want to do in your test environment. You want your test environment to crash early, crash hard, crash often. You want your production environment to have all of the performance optimizations to run as fast as possible and hopefully not crash as often, right? And so the combination of these two means that a series of classes of very subtle bugs will go from being things that are very hard to reproduce in production to things that always happen on your test environments. And if they always happen in your test environments, now you have a way of finding and fixing them, right? So always test UDFs, especially if you have stored procedures written with SPI and C. Always test those with enable cassert. Also SPI, which is the server programming interface. It's how we run SQL queries from C language stored procedures or user-defined functions. It does a whole bunch of memory context stuff behind your back. And this makes absolutely sure that if you've done something sideways, that you will get bit by it in testing rather than later in production. So just a quick look through an advanced topic, and then I'll probably take a round of questions if that's acceptable. And then go on to like actual examples. SPI, I mentioned, it's how we access SQL queries from C language user-defined functions. And it allows running, as I say, C queries directly in C. So it goes through shared memory instead of through a database connection and stuff like that. Where this uses memory contexts, it puts what we call the SPI stack in its own memory context under top memory context. It puts its own cached plans and so forth under top transaction context, under normal operations. But if you're in an implicit transaction because you don't have a top transaction context, it'll put it in portal context. And finally, when you go and you actually say, please persist this plan to cache, it will move the parent so it's under the cached context. So basically, each plan has its own memory context, and then as I say, it chooses the parent based upon when it creates the plan, it will create the plan either under top transaction or portal, and then when you tell it to cache, it'll change the parent. That's the actual code from Postgres. So if you want to see how that works. Now, I want to just kind of tell you sort of a war story really fast about this sort of thing. Some about a year ago, we were facing some segmentation faults in our largest Postgres instances. These are the ones that just do log analysis. We used to use Elasticsearch for this, but we moved to Postgres for scaling reasons. We spent a lot of time figuring this out. We found that it was a p-free related problem. We were passing a null pointer into p-free. And that this was happening when we were trying to free a cached plan because we wanted to invalidate that cache entry. What we found it was actually happening was when we went to plan a query, we might try to plan a query against a table that no longer existed. And because that happened, we would get an error. Postgres would effectively throw an exception using ereport. We'd have a non-local exit, and all of our checks for null pointers would never happen. So we'd go back to our list of cached plans. We would say this one should be cleared, and we would go and try to free it. The pointer to the plan would still be null. And we would free a null pointer and crash. That was a fun one to debug. It took us about 3 days to figure out what was going on. Partly because the error, the segmentation fault, would happen approximately 3 hours after we tried to plan the query that failed. So we have managed memory effectively. You don't typically do malloc and free. This is pretty high performance. It does most of the work for you. So if it's permissible now, I'd like to try to take maybe a round of questions and then go through examples on basic types. Is that possible? Does anybody have any questions so far?
So one extension PostgreSQL, and we have the experience that moving possible variables to the stack is faster than putting them as PLO.
So you're asking about why it is faster to put variables onto the stack than to use palloc and so forth. So what happens when we do palloc is we're going to start with our current memory context, and there's a whole bunch of machinery around this. We're going to then go to that. We're going to consult the free space map in it, and we're going to pull out a buffer on that. We're going to pull it out. There's a lot of machinery here. So yes, it's going to be slower than just passing things around on the stack. And in fact, when we go through our examples, we'll find that we tend to avoid passing things around from palloc, except when they come in or out.
So you think such a practice is good to never put to the stack?
The question is, do I think a practice is good to try to pass things around on the stack as much as possible? In general, when we're working on C, the stack is really, really, really useful. And it's generally good, I think, to have it do as much work still as it can. The thing is that when we write functions, we're going to have things that have to persist outside of the life cycle of that function. And then we have to use palloc, right? So again, the same thing about avoiding malloc. Yeah, sure, avoid palloc. But then again, that's just for performance reasons. That's not because you have trouble with when that's going to be freed. Any others? All right. So let's start with user-defined functions in C, and we'll talk about the boilerplate and what it's all there for, and where this can run you into trouble. And then we'll start to go through through some actual types. So first of all, user-defined functions in C are literally the building block of everything else. We can't do types without functions. We can't do aggregates without functions, and we certainly can't do foreign data wrappers without functions. In essence, with Postgres, everything is wrapped in functions, and so we absolutely have to be comfortable writing the functions in C before we can do anything else. So let's start with the most important piece of boilerplate, PG module magic. Anybody who's tried to do this before has certainly run into this. How many people here have actually looked up the macro definition? Nobody? Okay, so the macro definition basically just expands to a function that returns a particular structure with predefined stuff from other macros. Okay? Now, what this does effectively is it makes sure that all of the calling conventions and everything else are going to be compatible between the shared object we create and the Postgres instance that's making the calling. So basically, this creates a function that basically returns a whole bunch of compile time variables within Postgres to make sure that we can do that sanity check. Now, one of the things that it sends is the maximum number of function arguments that Postgres will ever send. This is set in the Postgres code from max index keys. I don't entirely know why those two are tied together in the way they are, but they are. So if you ever have a Postgres instance where you've had to change max index keys, this will break binary compatibility with compiled extensions. It also means that you can't take an extension that's compiled on Postgres 10 and run it with Postgres 11 without recompiling it, because those same sanity checks will all fail. Does that make sense? So this is solely about making sure that the sanity checks are all available. Now, why this is important is that we might have cases where we have somehow created a buffer overrun if we send in more arguments than the compiled extension was compiled to accept. So there are legitimate safety reasons for this. Now, if you are changing max index keys, this is probably not going to be a problem for you because you'll probably have all the infrastructure to recompile all your extensions for this anyway. If you're wondering if anybody ever does change max index keys, we do. So here are two examples of functions we use in a particular data type. And you're going to kind of wonder, I mean, the interesting thing about this is if you look at this, you can see it does kind of look like C, but there aren't a lot of words there that you recognize. So let's look at this again. What we're actually doing here is we're using a lot of C preprocessing macros to set up all the machinery around how functions can be called and things like that. So function info v1 creates a function, or it creates C code that basically makes sure that we append that Postgres can properly locate that country name and that it's set up with all the proper sanity checks. PG function args is a macro that specifies basically a struct that all the argument types come in. The getarg macros allow us to pull arguments out of PG function args. And we use those macros so that if something changes in Postgres, the implementation changes, our code doesn't have to change. And then the return macros basically wrap whatever we're returning in a datum and make that so that it's Postgres can then handle it, pass by reference or stuff like that. So how many people here have looked at this how many people here have looked at this trigger example in the Postgres docs? A few people have? How many people here feel like you understand the trigger example in the Postgres docs? Okay. I'll still go through it for everybody else. So, is this big enough, or do I need to make it bigger? All right. Is it? Is that better? Bigger yet? One more time? Oh, extend the window. Sure. There we go. So, okay, so now I have this big enough, hopefully everybody can read it. So first we have the includes. Postgres.h is a pretty no-brainer. It includes like the basic utility things that we need to interact with Postgres. fmgr.h is where all of these macros are defined. It's the function manager, so everything about how functions are invoked and stuff are tied there. Then triggers are the specific things around triggers. SPI, I mentioned what SPI was. This is what allows us to run queries from the trigger. And rel.h gives us the stuff around relations. So we've already talked about this PG module magic, right? So when we add this, it's going to add basically some stuff that allows Postgres to do all the sanity checks to make sure that this module is safe to use with the particular compiled version of Postgres that we're using. Here, we see basically the machinery necessary to register this function as callable from Postgres in that way. Datum is basically, from what I recall, a sort of void pointer, basically. It can be a pointer to almost any kind of item. And then, of course, PG function args is a macro that expands into the data type that our arguments come in as. Now, one of the things about triggers is a trigger basically is run in a very different context. Okay, we do not pass normal arguments into a trigger as such. Right, the trigger instead is given a context which gives the new row, the old row, the arguments that the defining trigger is passed in and stuff like that. Those don't come in PGR function args. Let's see. This is an extremely important set of lines. This calls a macro that makes sure we're running this as a trigger. And if that returns false, then we're going to elog an error. When we elog an error, this means we effectively throw an exception. We take them on local exit. Our appropriate memory contexts are cleaned up, usually up to the current transaction context, maybe up even the top transaction context, if we don't have a save point that we've rolled back to, and that sort of thing. Now we have some more. Now we have some more macros here that basically that allow us to inspect subfields of the triggered data that's been basically passed in. And you'll see here that the trigger is handled in fcinfo the context field of fcinfo. It's not handled, as I say, via the function args per se. So this is non-local state. It's important to keep in mind. Then we can make decisions based upon these macros. Did something happen before? Did something happen after? Again, one key thing about programming in Postgres is we end up having to use these macros a lot. Now, SPI context, this is all SPI stuff. SPI becomes very important anytime we need to run queries from our functions or such. And so basically, if we can't connect, we will throw an error. If we, then we can, of course, run queries. We can make decisions. I would typically not recommend, this doesn't look like this would perform very well if we end up with a lot of rows in t-test. We probably don't want to count them all every time we hit a trigger. Additionally, that plan is not cached. So not only will you have to replan, you'll also have to, you'll have to re-execute, you'll have to replan. So you probably don't, so that would be something which, well, it's fine as an example. It's a really contrived example, and you'd never ever want to do anything like that in production. Now we're going to log, or we're going to return as information. We're going to log as an information level how many rows we got, possibly, and then run the rest of this. You'll see again, we then return the returned tuple from a trigger, right? And that's as a datum. So datum can not only be a field, it could even be a whole tuple. Are there any immediate questions about this section? Okay, so major trigger gotchas. Cached plans may be invalid. If you cache a plan, which you can do with SPI cache plan, and you say, and there's a temporary table involved, next time you want to use it, it may be invalid. So there's the whole question of invalidating plans if you want to cache them. Cached plans can be null. You try to plan an invalid SQL query, and you'll throw an e-report of error. And when you throw that, you'll take a non-local exit, and you could end up with a null plan. If you end up with a null plan, you can't ever pre-free it. If you try to pre-free it, you will get a segmentation fault, as I described in the previous war story. And finally, you really need to use called as trigger, unless you really want to put a whole bunch of effort into making something runnable under multiple approaches. My recommendation in that case is it's better to modularize your code and just have a trigger function around the rest of it than it is to try to have something that can run if called as trigger returns false. So with that in mind, let's get on to the basic types. So why would we create basic types? We do a lot of basic types. We have tons and tons of basic types. I will go ahead and go through a couple of use cases that we have here. One of them is basically Postgres tuples are mostly handled as serialized structures, structs in C, right? So basically, you take the in-memory representation of the C struct, you may do some basic transformations to it, and then it goes out onto disk. You have a bunch of alignment things that have to go into making sure that's safe, right? So if you put in a 32-bit int and then a 64-bit int and then a 32-bit int and then a 64-bit int, it doesn't really matter how much space those are taking. Those are all going to take 64 bits, right? So if we can manage alignment better, we can save space. If we could do 32-bit, 32-bit, 64-bit, 64-bit, we've just saved 64 bits. That might not seem like a lot, but that's like a third of the actual tuple space in that example. And that's a contrived example, yes, but it's not uncommon to see a 10, 15, 20% savings by paying close attention to alignment. Now, a lot of alignment you could do just by reordering columns, but sometimes, if you can also save some space and you can go from variable length to fixed length, you might not only be able to manage alignment better, you might also be able to actually, get rid of, say, the variable length headers and things like that we'll talk about in a little bit. You could also do a bunch of really cool things. I don't know how many people here are planning on seeing Hickey's talk on Wednesday. I strongly recommend it if this is something that's of interest to you. He will cover a whole bunch of things that I'm not covering, including indexing and stuff like that. So in our basic types, typically a lot of stuff is going to be passed by value. Every type has a stored representation and a human representation, and the two are not necessarily the same. So in the country type that we'll look at in a moment, we have a human representation that's 2 characters, and a stored representation that's 1 byte. And that's a fixed length 1 byte representation. So we could put like 8 of those into the same space that we would use for a 64-bit int. By the way, that's really useful if you're doing like heavy data warehousing kinds of things, because this allows you to do something like a star schema, but to encode your dimensions as types instead of doing joins. And that can not only save you space all around, but it can actually make your queries a lot faster. So let's look at this example, and I want to go through a bunch of different pieces of it. I don't care if GitHub doesn't support this web browser. So let's start with the C code, and then let's look at the rest of it. Actually, yeah, because the C code's pretty basic, and you've already seen some of it. Then let's look at the packaging and how we declare it as a type. And then let's actually look at something that's really important and everybody forgets to look at, which are tests. So let's start with country.c, and then so you'll see here we include utils built-ins, and we include country.h. Let's just look at country.h quickly, and then we'll come back to country.c. Country.h includes countries.h, which is generated through some Ruby stuff we built, and then it includes basically the standard prototypes, right? Nothing major, nothing magical here. The only thing here is that Postgres does not have macros for 8-bit return types, so we added them. So that's not terribly so we have a function here called createString, which just does a palloc 0 and then a mem copy. We might be able to optimize this slightly by just doing a palloc and then a mem copy. Maybe a stir n copy might even be better, and then returning the string. The reason why I think that might be slightly better is that instead of zeroing out the whole thing and then writing it in, we could just write a null terminated string up to such and such characters. Which? Oh, you want me to make it bigger? Yes, let me do that. Control. Yeah. Okay. Okay. Oh. So now we have static inline country. Country from str. And we have the switch state case from, basically it just goes on and on and on. And you'll note that we don't have a lot more, so if countries decide to split up again, at some point we might end up having to rethink and find out maybe if some old country codes can be retired and replaced with something else. Which would not be good, but we still have 4 left, so. And by the way, I tested this. I couldn't find a way that was more performant than the case structure, by the way. This we might be able to make a little more performant, in that instead of switching, we could just have an array of pointers and take an offset. But again, very, very simple. These parts are basically an ability to translate, for example, to and then we wrap them in the Postgres function. So I showed these ones before. Here's what's really important to note here, is that these in and out functions basically translate human readable to machine readable and vice versa, right? So the code, in fact, may be ridiculously long but ridiculously simple, but the wrapping in it's actually really important. We have basically 4 that are really important. We have in, out, send, and receive. In, out are the most important because without them, we can't, for example, display properly or things like that. And so here we have, basically we convert the country 8-bit integer into a datum. And here we convert it from an 8-bit to a string and return that. Send and receive are then necessary for cases, I believe, these have to do with both parallel plans and sometimes get invoked when we're talking about storing to disk. And then we have some helper functions here. which basically allow us to do some utilities, so functions on these, so we can take a country name, we can get a full name, we can take common name, and we can get a full name, rather than just the 2-bit, the 2-character human representation. So instead of US, we could get United States of America. Instead of RU, we could get Russia. We could get Russian Federation, I think, under country name, and maybe Russia under a common name, if that makes sense. So in this case, as I say, a lot of the mechanics of it are very basic, but where things get a little more complicated is when we are packaging them up as a type for Postgres, and so that's the next thing I want to look at. So the actual packaging is not going to happen in the source directory because that's what creates the shared object. The actual packaging requires setting things up for the catalogs. And so this will be done via the extensions format and things like that. And we start by basically creating catalog records for all of our functions that we created. Now the interesting thing is C strings can be handled more or less directly as character pointers. We don't have to wrap them as text if we declare it as a C string coming in. Then country out returns country. No, return C string. Country receive, country send for byte A. And then we're going to create the type record. And basically, this type record here basically sets everything up such that we can properly handle, the Postgres knows how to store things and things like this. So input, output, functions, I think we've mentioned. Input is, you take the human readable, you turn it to the internal representation. Output, you turn it back into the human readable representation. Like means we're going to copy everything else from this type. How many here are familiar with the difference between car with double quotes and car without double quotes? Any hands? 1, 2, 3, 4, a few people. Few people are familiar with this. Car without double quotes is a variable length type, which when it is displayed is padded. With double quotes, it is a single character. So basically we're saying this is a 1-byte type. Make it like car. If I omitted those double quotes, we would have something very, very different. And then we have a comment. I strongly recommend putting comments on everything. Do you have a question? No? Okay. And then we'll create our basic utility functions in the same way. Now we actually have a type that can do all the basic things that we need it to. But now we have some other things we probably want to do. Anybody want to guess what this EQ, NE, LT, LE, GT, etc. is there for? Yes, comparison. These are all here for comparison. So if we want to say 2 countries are equal, we can just use the same function that we would use to compare 1-byte ints. Same thing all the way across the board. Less than, less or equal, greater than or equal, compare, hashing them, etc. Now, if you're writing these functions yourself, I'm going to tell you another great caution war story kind of thing. We had a problem where the planner was doing funny things on us. It was routinely choosing wrong plans, and thus we kept bumping the statistics up. We bumped the statistics up on these columns to 1,000, and it fixed the problem for a while. Then the problem came back, and we had to bump it up to 10,000, which is the max. The type we had was a custom type. It was a shortened timestamp, 1 second precision, valid since 2012. We spent a long time figuring out what the problem was, what the bug was.
Could you repeat the last sentence, please?
We spent a very long time figuring out what the problem was, what the bug was. We spent months on this. Finally, one of my colleagues, who will be here tomorrow, was looking at this, and he noticed that the GT function was mapped to the LT. What this meant was the planner was looking at the histogram it had of statistics, and it was traversing it the wrong direction. And if we didn't have high enough statistics targets, that we had every value in the statistics, it would make wildly inaccurate estimates and choose the wrong index every single time. So there's something you can learn from our experience if you ever see a custom type that just is behaving weird on the planner. Take a very close look at all these comparison functions and make sure, because these are not only used when you compare them like in a query, they're also used when you compare them on an index, they're used when you plan a query, they're used a whole bunch of different places. And then in the event where this is deployed to Postgres 9.6 or higher, we mark all of them parallel safe. We then create all of our operators. If you're creating any types, you want to create all your operators. An operator is just syntactic sugar around functions. And if you create the right operators, you will automatically get basic indexing support, things like B-trees, that sort of thing. Just in general, a little more complicated, but at least for B-tree indexes, all you have to do is create the operators and the operator classes, and away you go. So we create our operators. And then we create the B-tree operator class, which basically tells B-tree how to look at the operators. And we create a hash operator class for hash indexes, and then if we needed to, we could do it for Justinge and other things like that. How am I doing for time? Okay. So let's look at the next important thing here, tests. How many people here, show of hands, have worked with PG regress? 1, 2, few people here. Okay, how many people here have worked with PG regress to write tests for anything? So a significant number. I strongly recommend using PG regress on all of these. One thing we do at Adjust is we then run these on Travers, and we also run them on an internal Jenkins instance where we have a Postgres installation with CSRT enabled. That way, if something is funky, we hopefully crash that instance before we have problems on production. So what we're always going to do is we will see the expected bits here, right, for every test. And then we have the actual tests themselves in the SQL section. Normally what we do is we write the tests first, we run them, we make sure the results are sane, and then we save the output to the out file, and then everything's fine. When I look at people's extension code, one of the first things I look at is their test cases, because this gives me an idea of what they're thinking about testing and what they're worried about. For this sort of thing, there really isn't that much that we worry about, but you can see we have like country name, we have ops, so we want to make sure that that the operators work the way we expect them to and that sort of thing. And then parallel tests. Parallel tests were some of the first things that I did on these extensions, and most of them passed. A few of them crashed. Interestingly enough, none of them crashed due to parallel safety issues. When I'm looking at parallel plans, usually what I do is I actually output the plans and make sure that they're sane. This leads to another very interesting piece of behavior here that you'll want to be aware of when you work with this sort of thing. If explain crashes, the backend, but the queries normally run, this is usually due to a very specific error that is very easy for people to make when they're not used to programming in C. The most common cause of that crash is returning a string from the stack. Because that works until it doesn't, and usually in explain it doesn't. And then, of course, the persistence tests, where we write things in, we make sure we can read them. Very, very, very important. So before I go on, are there any questions? Just 1 second. I think they'll bring them. Are they going to bring the microphone over, or? Just go ahead and speak up, and then I will repeat your question. The wrong mapping in terms of less than versus greater than? So basically, what we had was an operator that we actually never used in production. So the question was, how did that error happen where we had the date time with the wrong function mapping in? What had happened was we had a function that we never used in production because we typically didn't typically query using that operator directly, but it was used by the planner when it made decisions about this sort of thing. So we actually hadn't included it in our test cases. We had not included it in our we had not included it in our test cases primarily. And so basically, I think it was LE instead of GE. No, wait, no, we always did bounded, so it was LT instead of GT. We had said, we had not put a test in for less than, we had put in for one for less than or equals to. But what was happening was, because we had a test for less than or equals to, because that's what we used, That all passed, but when the planner looked at less than, it would internally do all the comparisons wrong. Even though the B trees would work because the B trees themselves were using less than or equal to, but the less than was throwing the planner off, and it was causing it to assume that that it would generate a lot more rows than it would, and so it would try to use the wrong index in Travers. And as I say, the error was introduced before my time, but it took us a long time to find the problem once it cropped up. Apparently, people had been working around it for a year or more. Go ahead.
There is an example where a function takes an array as a and how to call such function and how to pass an array in binary mode.
Okay, so the question was, do I have an example of a function that takes in an array, processes it as an array, and do I have an example of how to pull in an array in binary mode? I don't have an example currently. I think I might on my next section. I have to double check. I think we might have something when it comes to the advanced types, but I need to double check that. Basically, you have the same approach of trying to use macros as much as you can, but there are a couple funky things about the way you would loop through arrays internally. So I'll try to get to that one in the next section. And any others? Okay. So let's talk about advanced types here. Now, the previous types are fairly simple. We have a very basic representation on disk. It's always the same length. And we could even pass that type around by value instead of by reference, right? We could pass an integer around. We don't have to pass a reference to the integer, right? Well, once we get beyond that, now we have some problems. This includes the fact that we may be dealing with variable length types. We might have to store variable length types on disk. And we might have to pass them around by reference because they might be complex, variable length, for example, lists of pointers or things like that. Both of these add some very important complexities. It's worth noting. The first one is the variable length header. Now, this is actually normally in the tuple header. It's not actually in the tuple itself. So when we store data on disk in a page, everything is what you might think of as an onion structure. We write to the outer, and then we work our way in, if that makes sense. The headers contain all the variable length information. Well, the tuples don't contain any of the headers. The tuples are just buffers that then get read into memory and processed via the header information itself. Several important things: nulls are referenced in the header. They're not in the tuple. And there are a bunch of other things, but the variable length bit's the most important. So you can't just pass in a struct and expect it to work. You'll probably just end up with corruption on disk and stuff like that. Pass by reference also has some really important gotchas. It's usually not safe to modify a pass by reference type value. So you can't pass references around and modify them because you don't always necessarily know what's going to happen behind the scenes or where that's going to go. So in general, when you want to change a type, no value, you're going to actually have to allocate again and change it. There are very, very few set of examples where that's safe. And then, of course, that means you also have much, much heavier use of send and receive functions, and the in and out ones are. So let's go ahead and look at an advanced type here. I'm going to look at a type that we have here. I will give you a basic description of what it's supposed to do. This is a type we call iStore. It's no relation to the Apple iStore. It's much, much, much closer to HStore. The idea of iStore is very simple. It's an integer to integer mapping, or an integer to big int mapping, or things like that. And the idea is then you can have a key to a value that's integers. We can then use this to model very sparse arrays. And we can also use it to, so basically you can say, you know, item 1 has such and such a value, item 3000 has such and such of a value, and item 6000 has such and such of a value, and we don't end up having to store all intermediate types, which intermediate entries, which we would in an array. Also, if we add two iStores together, we can collate on key and add the values. So we can say key 1 has this value, key 1 has this value, we're going to add those two together. This makes it very nice for things like time series modeling. It makes it very nice for modeling of anything else where we could maybe use a surrogate integer key or something like that. It's, of course, variable length. It's complex. We will look at different parts of the code and take a look at that here. So first, the header. Again, we include the function manager, the built-ins, stuff like that, memutils. We have all of our variable things. Now, in the event where we are compiling against Postgres 9.4 or less, no, less than 9.4, we redefine the function info macro so that we can properly handle all of this and register it. So there's an example of us actually overriding one of the macros. Typedef struct. And so basically what we've done is we've modeled this as a list of pairs where we also store the size, the number that are used, and the buffer length as a whole. So basically this is just a, it's basically a compact key value mapping for integers. For big iStores, we have a 32-bit key, but a 64-bit value. And then, of course, we have all of our prototypes, and then we have some special macros, which give us some nice things so that we can process things in our code without worrying quite about the implementation details in that part of the code. We also add our own macros for getting iStores themselves. And that's the, yeah. And then we have some more macros. So basically, this is again fairly heavy in terms of the sorts of things that we use macros for. And basically, we extend the whole approach of using macros quite a bit as we do this. So now let's actually look at the code. Okay, so basically, in this case, we're going to have a very large number of utility functions where we start with sort of the standard C coding approaches where we specify our arguments and things like that. And then we will, of course, wrap them with the Postgres wrappers later. You'll note here even the wrapping functions are much more complex. I'm trying to see a good example here. So here's an aggregate, I believe. Is that right? No, it's not an aggregate. It's a sum of the find. Let's see. This allows us to reference pieces. Does something exist? So forth. Now, one of the key things that you're going to see here is that we have a lot of cases where we just do PG return pointer. Basically, what this means is that we take the pointer to our current datum, and we just return it as a datum. That we're not going to go ahead and do any wrapping of one type in another and that sort of thing, like we would with uints and that sort of thing. So you asked about calling things from an array. In fact, we do have an example. This macro here, pg get arg array type p0. This allows us to pull the item in, the array in. And then we're going to have more. Macros that we have to use to make sure that we have correct types, that we have. And things like that. So if you're interested in examples of this, I would actually suggest looking at our iStore type and looking at that. So that would be one of the examples. Now, there are two other things that are worth, if people want to take some time and look at this code. We have a fully working implementation of GIN index support for the iStore. And basically what that means is that we can, you can do searches, which ones have the following keys, that sort of thing, right?
I still don't understand why you don't recommend to edit the class by value.
So the question is why I don't recommend doing the editing of the pass by value. The problem is that oftentimes when you're doing aggregates, depending upon what you're working with, their pointers, it's very, very, very easy to end up in a situation where you have overridden something sort of either in the wrong context or something else. So it's always strongly recommended if you're doing a lot of pass by value things to allocate them anew. Let me see if I can. There's a fair bit of documentation in the Postgres code and the Postgres documentation itself, which specifies, I think, 2 or 3 cases where it's safe to do so, and otherwise they don't guarantee it's safe. So if they don't guarantee it's safe, you could either return garbage, or you could, in worst case, you could be saving garbage, and you really don't want to be saving garbage in your database.
So the strategy is to initialize a new one, right?
Yeah, so exactly what you said. The strategy is to usually initialize a new one in a memory context that you control. And then in the cases where you can control it, then you can modify that out to the side and then return it back. Does that make sense? Okay. Now, I don't think I have a, I think as you can see here, there's a lot of stuff here relating to I/O and gin and stuff like that. I just want to call your attention to the iStore key gin, which is basically the piece that implements the gin indexing support. So if you're interested in sort of how that can be done, you'll see that it's about 100 lines of C. You can go ahead and look at it carefully. So again, the iStore type, I would recommend taking some time and looking at in some depth. Are there any other questions on the sort of advanced on these parts of the type? No? Okay. So aggregates, I'll go over the gotchas first, and then we can look at a very, very, very simple aggregate, one that we actually use at adjust, despite the fact that it's super simple.
Do you have to do a break?
Yes, let's do a break. Okay, yeah, I think it's fine. Let's take a break for I don't know, 10 minutes, 20 minutes. Okay. Perfect. We'll come back in 20 minutes. All right. So let's move on to aggregates. I have just a real simple. This is like brain dead simple. Maybe we want to go back and look at the iStore aggregates again as well. But we use this aggregate that is published by someone else. We have, of course, our own forked repo for it. But it's a extremely simple aggregate. I don't think you can possibly come up with any other simpler aggregate. We have one there's an aggregate called first and an aggregate called last, and it returns the first or the last in the group. So here you just have 2 extremely simple state functions, and since we're not actually doing any calculations, we don't actually end up necessarily needing to do a whole lot as far as memory allocations. And again, we just either return the first state or the last state, and that's it. So this is a ridiculously simple aggregate, and it shows that very simple things as far as aggregates go are actually fairly simple to do in C also. I think I want to go back and go through some of the aggregate stuff in iStore. Because one of the things that we do in iStore is we have some kind of important aggregates. And some of these are actually kind of important. And they're definitely not trivial. So if we look at iStore ag here, the last, actually just 1 second. We probably haven't touched this in a while since the last commit was add support for Postgres 9.2. So first, we have a macro that initiates the iStore state, and you're going to see here that in fact we do use agcheck call context, right? Because we need to actually set up something to store our data, and we want to make sure that that is allocated in the correct memory context. We want it to be allocated to the aggregate memory context. We don't want it allocated to the per row context, because then stuff breaks. And then we have all of the type defs that we need to for that state. And then what you'll see here is that, again, when we actually initialize the state, we initialize the state into the aggregate context. We do not initialize the state into just whatever our default memory context is at the moment, because there's a very, very good chance that that default memory context will in fact be the row memory context, and then bad things will happen. Bad things, you know, like corrupting what we're working on, and maybe crashing Postgres, and maybe other things. And I wouldn't even put it, you know, I wouldn't even put it past, you know, allocating the wrong context, even on a select query, as something that couldn't possibly cause some problems later in terms of, you know, if you possibly are doing some writing off of what you're selecting, you could also possibly corrupt what you're writing, even if it's not. Even if you're not writing that aggregated state out, because you could clobber something else. So the actual state bit here is slightly complex. But you can see that here we, basically what we've done is we've initialized the state off to the side, and now we can go ahead and modify it. But what we can't do is we can't modify anything that's in the per row state. And state extend here is an important function. I want to see if I have, the state extend itself also repallocs. This is very important because if we're going to extend the state, we want to make absolutely sure we're not clobbering something else in our aggregate context. That could happen if we have multiple aggregates running on the same query. We want to make sure we're safe on this, so we're going to repalloc. If we run out of space in one context, we'll allocate to another. And again, you know, the maximum size of a chunk is 1 gigabyte, so if you go above a gigabyte, you'll get errors. Anybody here ever hit the gigabyte palloc limit? Anybody? And another interesting tidbit from stuff that we've seen is, since we have a lot of software-generated queries, we actually have previously hit cases where the query was longer than 1 gigabyte, and Postgres said can't palloc the query buffer. So again, here we manage this. We extend the state if needed, if we see new pairs. And then we will basically reinitialize and copy again in so that everything's nicely ordered and easy to access, because typically we're not going to see new pairs all the time in the middle, and if we do, then we need to make sure that everything's set up for relatively fast access. Now, what this aggregate does is it takes these two integer mappings and is going to sum up the integers of the corresponding keys, right? So basically what we can do is we can, if we add an iStore that's 1 to 3,000, 32,400 to 8,000 and so forth, and we see many different cases where we have the key of 1, those keys of 1 will basically end up with a sum at the end. This is very, very useful because we can model a lot of things that we can then basically aggregate together at query time. So then the state accumulation is here. And basically, you can see that what we do is we do basically a merge aggregate within the type itself. So back to the major gotchas. In general, you do not want to modify pass-by-reference data that's outside of the aggregate memory context, because if you do, you could be modifying something that is somewhere else, gets changed out from under you, you get garbage. It is very possible to operate in the wrong memory context by accident. Even if you use all the functions I mentioned, if you don't allocate into the correct memory context, either by switching memory contexts or by allocating into a specific context, you will end up with stuff in the wrong place that will get freed out from under you. So always, always, always test with enable cassert. If you test with enable cassert, all these problems will always crash your test instance and therefore never crash your production instance. So are there any questions on the aggregate side? None? So besides types and triggers and functions, what else can we extend Postgres to do? Well, at Adjust, we have written several of our own Kafka several of our own foreign data wrappers, including one for Kafka and one for Parquet. What this allows us to do is it allows us to query data external to Postgres and use Postgres either for planning and executing queries, or for taking data from one source and joining it against data in another source. The possibilities with foreign data wrappers is actually very, very, very high. There are tons of things you can do with it. So I want to kind of go through two cases. I want to go through the use cases of them, and then we'll go through the code on both. Kafka foreign data wrapper allows us to read CSV or JSON from Kafka into Postgres as tables. And then it also allows us to take queries and write them to Kafka as streams of messages, either as JSON or as CSV. See a few people's eyes getting wider. Obviously, people can think of opportunities for using that, but you could, for example, read batches of messages, let's say 5,000 at a time, from Kafka into Postgres. You could join them into other things in Postgres and write them to tables. Or you could take tables representing events coming in, and you could generate data from those and write them to Kafka, which could then be processed by something else. And if you had, like, let's say, a very large number of Postgres instances doing this, you could actually generate a very large stream of data. So, or transform a very large stream of data or things like that. The second, which is also interesting, is the Parquet foreign data wrapper. We have a one of our service offerings runs on a database that right now is about 13 terabytes in size. It's still all on one system. We want to break it into many systems. We want to have elastic storage and elastic query capacity. So we decided to write all the data into Parquet files and query them in Postgres. We don't have to modify the data. We don't have to update it in Postgres. So therefore, we can just write it from, say, Spark or something, and we can query it this way. This ought to allow us to increase the amount of data we're serving 10 or 100 times, and basically be able to offer much, much richer services off of that data. If you're not familiar with Parquet, it's a columnar format, basically of column families, and then those get grouped into row families. And basically, it means that if you're doing analytics over large sections of rows on specific sets of columns, you can get very, very, very good performance compared to a row-oriented format like we see in Postgres. But it's immutable, it's not aimed at being updated, and so you definitely would not use it in a transactional framework. So let's go through these and just kind of go over the possibilities. Sorry. You'll see we do in fact maintain these. We have Postgres 12 support is the most recent things here. Now the Kafka foreign data wrapper itself is sort of interesting. One of the first things we have to do is we have to actually connect to Kafka, and we use RD Kafka for that. But we have to store those connections somewhere. So we chosen.
What is Kafka?
You can ask it. You want to ask again with a microphone? 1 second.
Excuse me. What is Kafka?
Oh, great question.
Some about it.
Yeah, so
Thank
what
you.
is Kafka? Kafka is a high-velocity message queue. The idea is you write into it on one side, and Kafka will break it into partitions internally, and you can read it out in parallel on each of those partitions. So basically, you can think of it as it's a message queue, but it internally parallelizes, and then consumers can read off of different pieces of those partitions serially. So all it is basically, you can think of it as a giant pipe of messages. And it basically, in our case, we have Kafka queues where we stream 1 million messages a second through. So we write 1 million JSON entries a second, and we have to read them out on the other side. So we connect to Kafka. We have to store those somewhere. We're going to store those in the top. Well, we store these currently in the top memory context. If I were doing this again today, I would store them in a memory context, which would be a child of the top memory context. Now, the foreign data wrapper handlers basically have a struct, which is basically a bunch of function pointers. So we define all the function pointers for doing all the different kinds of things. We attach them to the struct, and away we go. So you can see here we can define something that'll tell us the relation size, the foreign plans, how we explain the foreign scans, how we get statistics, for example, how we actually do reads, how we do writes, that sort of thing. Modify, of course, is for writes. That includes inserts, and then we do inserts. We cannot do updates or deletes in Kafka because, again, Kafka is just a message queue. You write in on one side and you read out on the other. And then we define all those functions. Let me take a look at this. Wait, source. Wait. What happened here? Hold on one second. Source. And then let's just do this. Alt, Control F. So you can see that the plans, of course, are all pallocked. We use palloc 0 a lot. I'm not sure that's always the best choice, but it's the way we do things. I think we have the actual connections in utils. In fact, I'm just going to search up here top memory context. Okay, did not show here. I'm not going to spend a lot of time searching for it, but basically when we create the connections to Kafka, we just store them in the top memory context, and then from there we use them generally throughout the reading operations. Would you like the microphone?
If I use top memory context, then probably the context will not be shared. It can be used only just for this session.
That's correct.
Yeah.
Yes.
Thank you.
Now, if you want it to be shared, then what you need to do is you need to allocate shared memory.
Mm-hmm.
And the only way you can allocate shared memory is in terms of something that's properly shared across all connections, is to do so at start. So then you have to use pre-loaded shared libraries to do that.
And is possible for data wrappers to use shared connect, or is the connect is just not shared?
It is possible to have shared connections.
Mm-hmm.
What you would have to do that is you'd have to have a preloaded shared library
Mm-hmm.
that would allocate that shared memory when the postmaster starts up. And then when you have the forked connections, they would all inherit all the bookkeeping around that and be able to locate it. And then within a memory context that they would know, you could then effectively have all the shared connections up there. But then you also have to note that if you're going to put the shared memories, the connections in a shared space, you're going to have semaphores or stuff like that to control access around them, and so you do have a lot more work to do there now that you're making them available for multiple connections.
Sure, but just when I do disconnect from Postgres, then I lost all further connects too if I use it in top memory context, but for this purpose, it's probably not a problem. Thank you.
Yeah, that is correct. Definitely, there is a trade-off there. In general, if connecting is light enough, you probably do want to just put it locally, because that avoids this whole concurrency topic. And then if it's not, then you need to take a look carefully at how you're handling that. Remember that a very large portion of the Postgres backend code is not thread safe. And so you have to ask questions about, are the libraries you're using thread safe? What happens if multiple, can you use worker threads for this? Can you not? How do you want to handle this? What happens if something's preempted? That sort of thing.
Thank you.
So, yeah. Are there any other questions on this bit here? Okay, so that's generally the. So I just want to come back to this one more time, because this is the essence of foreign data wrappers, and then we'll look at the Parquet foreign data wrapper also. Everything here is basically this FDW routine structure, which is just a structure of a whole bunch of function pointers. And so if you're writing a foreign data wrapper, basically all it is you're writing all the functions that are going to go into that struct, and then putting them in, and away you go. And in this case, again, we can insert, we can't update, we can't delete. So now let's look at the Parquet foreign data wrapper. Yep. Now, there are a few things that are interesting here. The first one is that while the Kafka foreign data wrapper is written in C, the Parquet foreign data wrapper has a whole bunch of C++ in it. Although I think we still say C for various reasons. Now, one of the things about C, C++ is that basically you have the whole include structures, the whole preprocessor structures are largely compatible. And you can write C++ that ends up looking a lot like C. The biggest difficulty is you end up with things like how do you handle exceptions? What happens if an exception is thrown? What's that going to do, and things like that. And as I was mentioning to somebody during the break, we've had, at Just in the time I've been there, so in 3 years, we've had 3 cases where we were having troubles with Postgres occasionally segfaulting. And when it was segfaulting, it wasn't the end of the world. Except that we did have half of the backends segfault once at once. So out of a fleet of 60 servers, you can imagine like 30 of them just crashing at the same moment because something went wrong with Kafka, and something, we hit an assertion failure, I think, in a C++ component of Libardi Kafka. So these sorts of issues happen. I have to figure out, yeah, so then we have Parquet implementation here that's in C++. So you have to figure out all these things. One of the basic things is you need to have that top level assertion, that top level, exception handler, so that you don't continue to bubble exceptions into Postgres, because then Postgres will die. And who here knows what happens when Postgres segfaults? Just a few, one or two? So if Postgres segfaults, things are handled in a remarkably sane way. If any Postgres backend segfaults, because we have shared resources, we have shared memory, we don't know entirely what happened. Postgres shuts down every other backend, reinitializes shared memory, and comes back, and enters into recovery mode, replays wall, comes back up. You can basically think of it as the database suddenly stopping and then recovering from a crash failure. That will roll back all concurrent transactions. Cancel all concurrent queries, everything like that. But that's the extent of it. So you tend to want to avoid that. But yeah, you can see here that we do in fact have a bit of C++ code that is then wrapped in the C code. And you can see this is all definitely C++ code. So if you want to spend some time later trying to figure out how to wrap C++ into the C for Postgres, that would be one that you could look at. Sure, you want just get the microphone.
I see the containers in your code. What memory context use these containers?
The containers.
Map, list, and other that you use in this function.
So, so the basic thing is you can palloc from any related language as long as you can access this. I think in these cases, if we're creating the Parquet state, these ought to be palloced into the statement or so context, because so in this case, in this foreign data wrapper, what we're actually doing is we're going out and reading a bunch of files, and in this case they're mostly on a networked file system like Ceph. We don't really need to persist these containers, so we would I believe I would have to ask the authors. I haven't contributed to this one directly, but I believe that these are under the either the statement or the top transaction context. We can't put them in the row, of course, but we can put them wherever else. And then, yeah, now we have the C interface functions. And these are the ones that do the wrapping. And basically we have two things that we're currently trying to do on this data on this foreign data wrapper, just if you're interested in it. The first one is making it so a single statement can query multiple Parquet files at once in parallel, and this would be multi-threaded. Then the second one would be trying to make it so that importing foreign schema could use a pluggable logic of some sort, so that if you have custom logic that says these are the files that should be mapped to a particular foreign table in Postgres, that can be effectively pluggable logic. So are there any general questions about writing or about the foreign data wrapper structures? I wouldn't expect that this would be the first thing that somebody would write against Postgres, but it's not that complicated. And if you take a look at a couple of the examples or the ones that we've looked at here, it's the first version of the Kafka foreign data wrapper, I think one of my colleagues put together in less than a week. So. See, how am I doing for time? All right. So in that case, I'll just open up to general questions. And if questions occur to you outside of this, you're welcome to reach out at the address there also. Sometimes they get buried, though, under cron messages. So general questions? No? Yes?
Sorry, my English. Kafka, maybe lost message.
Okay.
What? And storage in memory. What? Million message там by second. Да, я могу по-русски.
I can speak in Russian if you don't mind.
Just in Kafka.
Yes, it is. Okay, so with Kafka, something to be aware of is, there are different ways you could lose messages, but the most common thing is that Kafka has a defined retention, and if you don't read the message in time, it's gone. That's the key. That's the most important thing. When Kafka says it's committed, it has in fact committed to disk, so you won't lose it at that point. But so for example, we have a lot of cases where we read from Kafka, but we have a 30-day retention, and if we're down for reading from Kafka for long enough, the data's just lost. Yeah, but it's okay. So there are also a bunch of other configuration things. It is possible to also lose them on the writing side if you've misconfigured things. But if you have things configured correctly, you should, and you don't want to lose messages. That's a key thing, because you could configure it because maybe losing messages isn't a problem. But if you've configured it correctly, the only reason why you should lose messages is at the end of the retention period. We have another question here.
Maybe we should do a presentation on Kafka later.
Yeah.
What about ACID principles at all using Kafka and FDV? If I'm not mistaken, it seems that you do two selects in same transaction, you may get different results. So what about ACID?
So once you start doing foreign data wrappers, you're going to have to think about the concurrency and consistency models that you're working with. Now, within Kafka, the way we handle things is you specify a partition and you specify an offset. And when that query runs, you should get the same results as long as you're within the retention period. The difficulty is if you also, as I say, there are other ways that you could, there are other ways in which you could configure things, of course, and there are other ways you could use it. But at least in terms of the ways that we have configured and used it, we don't have that ACID problem with Kafka. Again, we have successive queries that increment that offset. But as long as you're incrementing the offset, you're moving from one consistent state to another, right? You're not going to run the same query multiple times and it's doing hidden things behind the scenes. But that's sort of a separate question.
Are there any more questions?
Any more?
There will be a comment to the question. So probably just a comment to this question. Kafka is actually a messaging system which stores a living stream of data.
Yeah.
So what you do is you store each additional change of a state of something. For example, light. Light is on, light is off. And instead of overwriting previous data, what you do is you store a new message with a new timestamp, kind of. So ACID compliance is not applicable here. So what you do is you're kind of, in terms of Kafka, you're working with side effects. So wherever you query your data, you can either you're asking for the status for a certain period of time. That's what he has suggested. Or you want to know the actual status. And in that terms, you don't actually wait for durability, consistency, isolation. You just want to know, hey, what's going on?
Yeah, and it's also worth noting that Kafka's concept of isolation is an internal concept of partitioning. So basically what happens is Kafka divides things into partitions, and the idea is that you can read in parallel off of each partition. So that's its concept of isolation. And once it's decided that this message is in this partition, it's always there. Well, that also means that you can't read off of partition 1 and partition 2 and expect them to have the same data. So this is something that happens anytime you're doing foreign data wrapper stuff, is that you're going to have conceptual mismatches of what exactly consistency means, what exactly isolation means, and some of these other sorts of things. And so when you're going ahead and using them, it's important to remember that you're going to get within the database, within Postgres, a very tight interpretation of ACID. But within the foreign data wrapper, you might not. I mean, if you're using the CSV the file foreign data wrapper and you're writing CSV, you're not going to have the same isolation and consistency guarantees that you will with the standard Postgres tables, for example. And this is just a fact of life of working with foreign data as a whole. Your consistency guarantees and such are dependent upon the other side.
Okay, I have a question myself.
Okay.
We are doing database monitoring, and we want to count number of errors and warnings and internal errors with corruption signs in Postgres logs. So we can read from log files, or we can create a C extension and hook to login hook and count errors and warnings there. What would you recommend? Reading file every time from a disk and counting these errors and warnings, or doing log analyze inside e-log and e-report hooks?
Okay, so I haven't dug completely through all of the e-report and e-log code all the way back. So this is just my intuition. And it may be that there aren't sufficient hooks for this. But the two things I would look at is whether there are hooks in that section of the code that one can easily just hook into. And if so, I would use those. And the other thing I would look at would be is if there are dynamic trace points that give you insight into the metrics that you're using, because the disadvantage with some of the dynamic trace points is sometimes
what is dynamic trace points?
Oh.
Right.
So Postgres has this system of dynamic trace points that you can look at number of transactions that have happened and things like that by just simply asking, basically asking for example, using IBPF or some of these other frameworks. This is kind of a big topic. Maybe we want to take it off of this. Outside of this, but that would actually be outside of Postgres. That would be another process, basically asking Postgres, hey, could you send me data when these things happen?
Okay, so the basic answer is Google for dynamic trace points.
Yeah.
Thanks, makes sense. Do we have any more questions? So probably let's thank Chris. Wait. We have more questions.
So if I want to create a C extension
Yeah.
on my on-host server, I will not have any questions. Is there a way how I could create a C-based extension in AVS? Is there a way to group the C code into PSQL? I don't know.
Okay, so let's start by, this is one thing I actually didn't cover in this training that I probably should have, and that's the basic concept of the Postgres security model in this regard. In order to define a C language function, you have to be super user.
I am a super user in
right.
AVS, but I don't have access to the shell.
Right.
I just have access to my Postgres environment.
Let me go through what I mean by all of this, because if you are a complete database super user, you have shell access. It might not say that you have shell access, but if you are a database super user, you have shell access. That means that you could, for example, copy from program wget. Basically, that's the point I'm trying to make here, is that if you are super user in Postgres, and I mean real super user, I don't mean RDS super user, because that's something else. If you are a real super user, you have shell access. I actually, one of my colleagues was having trouble with SSH not working because of an issue where we were having syslog failures, and then SSH couldn't connect because syslog would fill up. So he actually did copy from program using netcat and bash to get himself an interactive shell. So yeah, BusyBox, netcat, and bash. He was able to just use those, copy from program, got an interactive shell. So, like if you're using RDS, you can't extend with C because they won't give you super user. They do not want that support burden. If you are using AWS EC2, then you can have a full database super user. But that's the line that's drawn.
Thanks.
If you have a super user in RDS, you probably can report them as security vulnerability, I think. But by the way, I don't think that you can actually use netcat for querying Postgres, because Postgres protocol is quite complex to do it in.
No, he used copy from program along with BusyBox and Netcat and Bash, to be able to then use Netcat on the other side and get access to Bash.
He used PSQL to run a SQL query copy from program, which executed program, which returned results back as a result of a SQL query.
No, he used it to open up a shell that he could access via Netcat, and then would report the result of that as a SQL query.
Okay.
So, yeah.
So, do we have more questions? Anyone? So, finally, it's time to thank Chris.
Thanks.
Thank you very much.